And welcome to more Acoustics. How do you feel?
Great.
Let me hear you say, yeah.
Woo!
Excellent.
Buildings.
Huh? Buildings. Cool. So there won't be many surprises in terms of structure, but I hope in terms of content, I won't fail with keeping you on your toes, excited and interested and all the rest of that. So as usual, let's first discuss the bits from last week. Anyone wants to come forward with some wisdom that they have acquired in the meanwhile? Well, to me, two things are really interesting. First of all was the port. That's the most interesting thing to me. And some of you know it, but I'll just repeat it because we had 3 groups in 3 different rooms. And they were actually well distributed along the axis of size and treatment. Okay, so we had people in here, no treatment, quite large. We had people in 88. No, people in 44, right? So quite large, but treated. Okay, this was the kind of the middle case. And then we had people, was it 88? I think it was 88, yeah, which was small and treated. Okay, and the interesting thing was that people in here, in 71, measured 100 millisecond difference in terms of the decay time at the frequency of the port, right? So you remember the experiment went as follows. You had a speaker, you measured the response in the room with the microphone at the given positions. I'll try to repeat these 5-6 variables every time just to keep you on your toes, hopefully. And then the same thing was done with plugging the port. By the way, I didn't really inquire into how you plug the port, which could make a huge difference, by the way. So obviously, typically when I plug my ports, no pun intended, what I do is I try different density materials and different thickness. I typically do plug my ports, if there are any. So don't laugh. So, and it's actually quite similar. I don't know if you're at all into ale beer technology. You know, art technology comes close, yeah? So what they have actually is they also have plugs, and they have a port in the barrel, and they actually have different density plugs, which controls the amount of oxygen coming into the barrel, which controls, on the other hand, the speed of fermentation. And as they open the barrel, they start the second fermentation, blah, blah, and so on and so forth. We can discuss ale technology at a later point. But it is actually crucial how you plug the port. So if you play with this, you will find that, you know, totally sealing the port will have a different effect from just plugging it with sponge, with, you know, socks or whatever you may come up with. What did you plug the port with, by the way?
Toilet roll.
What?
Toilet roll.
Toilet roll. Interesting. Well, was it like you actually made a wee ball of bog roll, a wee roll of bog roll? Sounds like a band name or maybe an album. Now, so that was the interesting thing. So in here, sorry, did I say the other way around? So in the smallest room, the treated room, the guys measured 100 milliseconds. Here, people did not measure the effect of the plugged hole. Why on earth? And by the way, in 44 middle way, they kind of got about 50 milliseconds measurement going. So the point is, I mean, there could be multiple reasons. Obviously, we didn't meticulously check the method of measurement and plugging and all the rest. But the thing that we can resort to easily in terms of explanation is that in this room, the decay times at those frequencies are already such that the additional 100 millisecond from the port did not show up on the measurement. Make sense? Right? So if you have a well-controlled room where the base decay times are low, then the port will be measurable. Now, whether it's audible or not, that's a different topic altogether. But in fact, I will, increasingly ask you to also assess things with audition, right? In the assessment brief, each task has something about audition, just to balance, this paradigm that, we can measure things and that gives us certainty. Again, with the dimensions of a desk, measurement does give us a great degree of certainty. With acoustics, not necessarily. Okay, so this audition will be quite interesting. Cool, so we did notice the problem with the port. Now, remind me what happened with the character of reverberation in 3 radically distinct spots. Does anyone want to share their conclusions on this? So typically what was obvious for all the groups, as far as I remember, is that the speakers placed in corners against the wall near reflective boundaries gave us measurements with longer decay times. Okay, so you could say more reverberation. Now that's an interesting topic. What does more reverberation mean?
Longer reverb trials.
Does it? What'd you say?
More trials. Instead of the trials being longer.
What is
more reflection?
Turbo? Well, the thing is, that's the interesting thing. That we have a way of communicating, in this context of music tech, and typically, if we say more reverb, you might think that it will be a longer decay time. But technically, we'll probably avoid the word more and said increased gain of reflections, right? Or longer reverberation time. Okay, so I invite you to critically approach, the language that you're using and try to be more specific and more accurate and, greater, more. Again, you could be thinking about density, you could be thinking about a lot of things, and especially because you are working on your projects where there is a likely amount of tech embedded, think about the terms that you use, because if you use an overly generic term, you might be saying more than you intend to, right? So I would typically avoid saying the word more reverb altogether, right? Because I can be more specific about which aspect of reverberation I am discussing. Okay, cool. So that was the radically distinct spots. I think everyone has seen that, bass just rings on regardless. Yeah? Compared to mids, compared to highs, bass just does ring on. What are the issues with this?
Correct standing wave.
Well, that's kind of the reason, right? Because the standing wave is there. What does it mean? It actually means why. So if we talk maybe a bit of physics here, so how on earth, what's the relationship there? So I have a standing wave, fine. Do you remember the difference between the standing wave and the running wave? You remember my little, because no wave is really standing, right? It's a kind of a misnomer if you ask me. But what happens is that if I have a traveling wave, right, I imagine a long cord of 20 meters, which is tensioned, and I produce a quick disturbance at one end, and I will actually see the little disturbance travel. So that's how you can imagine a traveling wave, that the disturbance actually travels forth and then probably reflects back. By the way, interesting for some of you potentially is that it can reflect back in 2 ways. You have a phase inverting reflection and you have a phase preserving reflection. Very interesting. Any idea what would be the 2 options in this specific case?
When no disturbance isn't travelling both directions.
That's a slightly different thing. It actually has to do whether the end, the termination, is fixed or not, right? So if it's a fixed termination and the wave comes traveling upwards, so to speak, peaking, it will reflect bulging.
What do you mean by fixed termination?
Well, I mean, I can't really imagine a tangent chord which is not fixed at the end.
Yeah.
It's kind of difficult. But if you do, or if you imagine a ruler, you know, if you fix the end, you will get a different type of reflection from not fixing the end. This is just on the side of everything as a matter of exciting things. But back to the point here. So traveling wave and standing wave. So what is it about the standing wave that is apparently standing? Well, it is the fact that the bulging and the dipping does not seem to travel, and again seem, but seems to stand in a certain position and just go up and down. Okay? And this actually there's some really nice physics simulators online. If you watch the theoretical lectures, I will refer to those. But actually you can see that quite well, that if you have a wave traveling and reflecting, and that wave is of a certain frequency, then the reflection actually gets to constructively interfere with the newly incoming wavefront, so to speak, right? So actually the reflection and the thing coming forward constructively interfere due to the relationship between the frequency and the distance, right? That kind of makes sense. Okay, so standing wave. So let's think about this. So if I have a standing wave, why on earth does it ring on?
Reflecting back and forwards of two surfaces. So it doesn't disperse.
That's the word. Yeah, the dispersion of energy is different, right? That's something you can consider. Okay, I don't want to get too theoretical, although it's inevitable. Anything else about the reverberation that you have noticed in the rooms? That you have looked at? Main message is probably you've seen that the bass rings on like crazy. If you want a balanced decay time across the frequency spectrum, which is typically what you do want in a control room, then try to avoid dampening highs and mids while increasing the dampening of the low frequencies. Okay? So curtains, things like this, thin absorbers, they will actually tackle mids and highs, and it will actually give you a larger disbalance in the profile of your reverberation. Cool. Excellent. And then finally, estimate the influence of an absorber placed behind the microphone. Any wisdom coming out of this one? So the limited.
That were coming back.
Yeah, it wasn't huge.
No, it wasn't.
It wasn't huge. I think, again, the conclusion was that in an untreated large space, it was more obvious. Yeah? But in a control room, treated, fairly small, it was not noticeable. Am I right to say this?
You just put in like panels in a room, acoustic panels in a room already full of acoustic panels, aren't you?
Very true. Very true. Okay, so what would be, let's say this is a practical, well, it is, only it's fake, but it is practical. You're in a situation where this is to be decided whether time will be spent with dampening or placing absorbers around microphones, okay? So you're the engineer, and the guy comes in the studio and he says, well, I've got all the cash in the world, so there's no time constraint, but I have heard that placing absorption around the microphone can help. Can we please investigate this? Okay, and you're the engineer, and you say, well, obviously, at your service, I shall now show you the measurement of the difference between this and that, and here it is. And the guy says, oh, it seems like it does not make a difference. That is rather odd. What is your reaction? Is there any other way of further investigating this? And I've already mentioned it 5 minutes ago. And it's always to be considered and probably with priority in relation to measurement, it is audition. Just listen, okay? So you have the measurement, great, that says one thing. Then there is the audition. Okay, let's listen to the two options, right? Makes sense. How do you listen? Very important, blind, okay? So if anyone, including myself, knows what they're listening to and what they have paid for the certain bit of gear, they are inclined, and it's measurable, to consider that sounding better, right? So you may not consider a listening test valid if the subject knows what they are listening to. So you have to prepare a blind listening A/B test, and it's really useful if the subject can switch between A and B themselves and spend the amount of time they find necessary. Okay, blind testing. Okay, from this comes the result. We're still in the same scenario. From this comes the result. Well, I think I hear the difference, but A/B testing has shown that my guesses are as good as random. There is no significance to my estimation of better or worse. Okay, but the client is still not very satisfied. But wait a minute, is there actually no reason to put absorption around microphones at all? What is your response? And now you have to think out of the box. Snare roll. Crosstalk. Then you can tell your client, well, actually, as soon as there are multiple microphones in the room recording, then crosstalk will be happening, and then actually all the reflections might act destructively or constructively, in any case, in an anomalous fashion. Okay? So what do you do then? Well, you set up 5 microphones the way they want them on different cabs, guitars, whatever is being recorded, and then you actually look at the summation of the 5 microphone signals with or without absorption around the microphones. And then, well, I propose, who knows, you can do it. It's a bit complicated to set it a task for the practical, but there could be what? How would I hear the anomalies, if there are any?
You hear it in the mix, wouldn't you?
Yeah, how? What do I recognize? How do I, describe what I'm hearing if I'm hearing that type of anomaly? Say again? Comb filtering, exactly. And if my client does not know the term comb filtering, what is the other kind of set of terms that he might be using? Well, visually you can appreciate it. You can say something like, it does not sound full. Okay? The other thing, if the instrument is moving, then you might hear the notches move up and down. So the client might call this phasing. Okay? So there could be anomalies in that department as well. Okay? Cool. So actually, slowly we are getting onto the topic for today, which is reflections. And I've already said it, I believe, last time as well. In fact, I've kind of shortened the thing, although I thought last week was exceptionally pleasurable to see how quickly everyone is getting around these measurements already. So do please again consider selecting the more passive team members to do the more active bits. It's good for them, and maybe for you as well. So reflection. So I've announced this, that there should be a way, and this is going to be the main thing today, for us to distinguish between anomalies that are due to the room itself and the anomalies that are due to the positions of sources and receivers in the room. Okay, anyone remember how could we potentially make the difference? So the difference should be in that room modes do not change frequency unless the walls are moving. Okay, that should be straightforward. If the walls are not moving and there is no large objects being moved in funny ways or less entertaining ways, then we don't expect any frequencies to change. If the microphones and the speakers are moving within the room, on the contrary, we do expect to see changing frequencies of what? Notches and peaks. Okay? So there should be notches, which is destructive interference due to reflections. There should be peaks, which is due to constructive interference. Okay? So actually, you will be moving stuff. And when you're moving stuff, you'll probably appreciate that the real-time engines are really useful, especially when you work in a group and someone can move the thing, someone can watch this or that and report accordingly. Okay, now I will first briefly explain this comb filter arising. Okay, is that of any interest? It's a kind of a theoretical chapter. I'll try to get the board, but I think it's really, really useful to see. I hope I will remember to resize the things accordingly. So, how does this look like? The crucial term, if you want to acquire fancy terminology, is path difference. I think I've used this word already. I've actually suffered an injury yesterday, and my right hand is a bit out of order. I didn't beat anyone to death, by the way. The asphalt beat me a bit. So, what are we looking at? We're looking at path difference. Okay, so the basic situation is that I have a speaker projecting to a person. That's a person, that's the ears, losing hair, whatever. Okay, so there is the direct path and there is the reflected path. Right? This, again, please do acquire fancy terminology. Anyone knows how do we call a normal reflection? We call it a specular reflection. Okay? Which means that the angle of incidence is the same as the angle of reflection. Okay? So I was actually thinking to try and set up something like this. We'll see if you guys are really motivated and done with the first two tasks. We can work this one out. And actually I was thinking that the easiest thing will be potentially to take a desk like this. I mean, obviously you have these angle measurement things. Ooh, that's not good. And then if you place it against the wall, you can kind of make sure that the 90, this is 90 degrees, such that the wall is normal against this middle line. And then you are sure to know the exact distances. But obviously you can just place things randomly and then measure. The thing being that we've tried this before, and it doesn't appear to be very clear or indeed to match the exact calculation. So I won't even go into this, but the important thing here is that I can model this, I can think of this situation as follows. I have the incident sound at the receiver, and then the reflected sound at the receiver I can think of as being delayed. Fairly straightforward. Now, you probably know this already, but if I sum these two signals, which is typically what happens at the point of the receiver, then this may cause constructive or destructive interference. And what else? Phase changing, okay? So you can kind of visually do this, and it won't be off by too much. Actually, if the peaks are almost aligned, like in this case, this seems to be the time difference between the peaks, that looks like a constructive interference, okay? Now, what you are actually doing then is you can pretty much interpolate between the phase. So you can actually call the peak somewhere here, between those two. That's pretty much how it works. And then obviously if that's all the same frequency, it will look a bit like this. Now in terms of amplitude, obviously if it is full constructive interference, it will double. If it is destructive, it will zero itself out. This is somewhere in between. I'm not horribly fussed. Now, the question here is, can we come up with a spectral plot that describes the characteristic of this path difference? Okay, so I'm going to call this a path difference situation and assume that you're summing it all in the end. So if I have a path difference, what is the spectral characteristic? That's the question. Okay, so let's try to devise this. Well, first of all, let's say I have a fixed delay time. Okay, shall we do numbers? Let's do 10 milliseconds. Can we figure out what would be the path difference in meters that causes a 10 millisecond delay of the reflected path? A bit of math. I mean, obviously you won't be asked to perform this math, but I do think it's a good thing in terms of developing your intuition. So one thing you probably remember is that 340 meters per second is the speed of sound in air in certain circumstances, which means that in order to travel 1 meter, how much time do I need? 1 over 340 seconds. Okay. Now, 10 milliseconds, on the other hand, is 1 over 100 seconds. Can we figure this one out? Back and forth. So what do I expect to be the distance that causes 10 millisecond delay?
35 centimeters.
I think that's probably about right. Yeah? Shall we go through this? So what I'm saying is that this is the distance, right, which is 1/100th of a meter, right? And 1 meter will take this amount of seconds. Okay? Does that compute? So actually what you can also probably remember as a kind of a rule of thumb, yeah, is that if you have 1 meter distance, right, what is the frequency that corresponds to that 1 meter? It is 300-400 hertz. You see it here already, 1 over 340 seconds, right? So if I decrease this distance, what happens to the frequency?
Decrease or increase?
I decrease, I shorten the distance. Well, it's a higher frequency, right? Shorter wavelengths give higher frequencies. Okay? So what do we come up with here? Actually, what's going on, I'll probably leave the numbers behind. I see a few puzzled faces, I don't want to push this. The point that I'm trying to get to is that there will be one frequency at which we will get a full constructive interference, and that is the frequency that corresponds exactly to a full period. So 10 milliseconds has a full period of 100 hertz. So at 100 hertz, I expect a peak on my spectrum, which is supposed to describe this path difference. Now, if I have a frequency which has a half period corresponding to 10 milliseconds, which frequency is that? So I double the period, frequency is half, so that's 50 hertz, And what do I get at 50 hertz? If this is the original wave, it's moved by exactly half the period. I get full destructive interference. That's what it is.
So you get a peak at 100 hertz.
Yeah.
And you'll get full destruction
Yeah.
at
50.
That's a proper peak. Will
And-
that repeat in the series?
And that's what we're getting to, exactly. So the point is that these are the lowest, and actually we could also discuss what happens below 50 hertz. What happens at 25 hertz?
You do it again.
No, at 25 hertz it's even lower, right? So actually this delay time will become increasingly constructive. I mean, at a 0 hertz, it is actually fully constructive back again, right? So actually what we get here, and obviously at 25, you will get some kind of constructiveness, so the graph looks like this towards the 0 hertz. Now the nice thing is obviously I can try to draw this, although it might not be helping. But actually as the frequencies increase, right, this means that the wavelengths are increasing further, right? You will see that periodically I will get notches and peaks. In fact, I get a notch at half, 1.5, 2.5, or in other words, half, 3/2, 5/2, 7/2, and so forth. So each of these frequencies will give me a notch, and frequencies in between will get a peak. So I hope this has served some intuition development, but this is a kind of a way to explain and hopefully to remember that any path difference that you come up with will have a comp filter as its spectral characteristic. Cool. Now, the good news is that this is horrible only if there is a single specular reflection in this scenario. And these scenarios are very rare, because what you would have to do in that case is you would have to be in an anechoic chamber, which means everything around is fully absorbed, and you place one reflective surface and then do the math, and then it should compute. So probably the reason why it doesn't really compute very well, although you will try, hopefully, is that the amount of reflections is such that you have huge amount of comp filters all over the place, and they actually neatly average out, right? So the more reflections, the more these anomalies will be averaged out. Okay? Cool. So that's your reflection explanation. So let's see what we've got left. I think the thing that's left at this stage will be to look at the REW and show you the bits that you will need today. Okay, so what we're gonna deal with to start with as a first task will be estimating the room resonances. Okay, so I've clicked, I don't know if that went a bit too fast, but up here, top right, there is a room sim button. And this invokes the room simulation. I will restore to default settings, which did not restore all the settings, but there we go. Because typically when you run it, you will see many graphs like this. So what I suggest is you remove those altogether. So first of all, I will just look at the room modes, which are currently not on display. So what you have here is a few tabs, so to speak, and the first one is modal resonance lines. And here I can choose to see the modes of the axial length. So we have three types of room modes: axial, tangential, and oblique. And this has to do with the number of surfaces that the wavefront has reflected off of. Okay, so the axial mode is the simplest one because it actually reflects only between two parallel surfaces. Okay, so this is the mode that comes to exist between parallel walls. As soon as the walls are not parallel, it is likely that there will be another reflection involved. So this is a fairly straightforward and strict thing. So what I will ask you to do is to model the room that you will be in, and you can enter the length, width, and the height right here in meters. And then you can see the modes. So the axial modes, there's 3 of them, and they correspond to the 3 dimensions that you have just entered. You can play with that a bit to see them move, for example, right? So if I'm increasing 1 dimension, then the modes corresponding are becoming lower in frequency, right? Larger space, lower frequency. Okay, so you can see them move. Now, what you see as well, you can kind of pinpoint them, so you can read that this is at 31.3 hertz. You will also notice that they have harmonics, so to speak. So every integer multiple of that frequency will also act as a resonant frequency in the room. Now, as you see, we are looking only until 200 hertz. If I was to increase the range here, you would see that the amount of modes, the density of modes is increasing hugely. And again, we get a kind of an averaging out effect. So actually, we're not very worried about modes above a certain limit. 200 hertz is probably generous as well. Okay? Because these few low frequency modes are the most problematic because they will boom, because if there is a bass note hitting that frequency and you don't hear it, you're going to crank it up. If it's hitting that frequency and it's too loud, you're going to make it softer. The mix won't translate, and so on and so forth. Okay, so these lower frequency modal anomalies are of great interest. Okay, now the point of the bit here is that, you can do this, do the measurement, check these modes. I suggest that you click them on and off just so you see what's going on and see what you're looking at. I will ask you to identify 6 first order modes. Okay, so the first order means that it is the fundamental frequency, so you're not looking at higher harmonics, so to speak. So the tangential length width mode actually resonates at 53 hertz. Okay, so you note that down. So I'll ask you to do that for all the 6 modes here. Take the lowest frequency, note it down. And then what I'm asking you to do is to actually listen to those frequencies and pinpoint them. Okay, so this is an estimation. The value will vary. The actual value in the space will vary based on reflectiveness, based on some anomalies, obstacles in the way. There could be different things. You could get, a ventilation duct bouncing it back at you, counter phase, does something unexpected. Suddenly the mode is not visible, it's not there. So what I will ask you is estimate these 6 frequencies based on measuring the room and then audition them. So in order to audition them, you can easily use the generator here. You can get a tone, you can get a sine wave, and you can actually change the frequency with little values, small values, such that you pinpoint the exact frequency. Now, as you know already, you've listened to sine waves in a room. At every position in the room, you will have a different loudness of the sine wave, right? So the best way to do this is to have one person moving the frequency just a bit up, just a bit down, and the rest of the group spread in the room, telling the person at the computer, I think I've got it. This is definitely resonant, right? And you can also move in the room. So you have multiple pairs of ears, multiple positions simultaneously, and that is very helpful. Because if you would try to do this with a single microphone, it would deceive you. because the very position in the room that you're measuring will contribute a huge amount to the presence of this mode. Okay? So distribute the team in the room as much as you can and ask everyone, okay, is this the resonant frequency? And if you think it is, then the people in the room can walk about, right? And if you walk about, what you actually expect is that you will have deeper troughs as well as higher peaks. You see, because if it's not a room mode and you walk around, you will have some variance in the perceived amplitude. But if you hit the mode, then you should have a null in the room as well, right? Which otherwise wouldn't be as obvious. Okay, so that's the idea, that you actually go to through the steps of getting a room model, then note the nodes, first order nodes, 6 of those, modes, sorry. Then, in order to assess the room characteristic, in order to pinpoint these modes, I suggest you put the speaker in the very corner on the floor in the room. Because in this fashion, you are sure to drive the room as much as possible. Okay? So you will notice that obviously the sound is horrible. You don't want to listen to music when the speaker is in the corner of the room. But when you want to drive the room and explore the resonances of the room, it is the best position. Okay? So speaker in the corner, and then one person slightly adjusting the frequencies based on what is estimated, and see how many of them can you actually identify. Okay, this is definitely a room mode, and see how many of these will, what will be the values, what is the difference to the estimation. Okay, I will be curious about this. Okay, so this is the first half, figure the modes of the room, and then the second half will be this dipping and potentially peaking, but I've just put in dipping for now. Obviously, I've already seen groups go further than what is specified. You're always welcome to. But as a basic exercise, let us try to identify these dips. Okay, so I've already mentioned that probably a good idea is to take a real-time analyzer and play pink noise through the speaker. So I imagine a microphone in a fixed position, and one person, luckily the generics are fairly small, silently as much as possible, moving back and forth in relation to the wall. And as they do this, you are likely to see a notch moving up and down in frequency. Okay? As a matter of experiment, once you identify the mode of the room, by the way, you could also take the speaker out of the corner and move it about, and you should see that mode go up and down in gain, but not in frequency, right? So that's, again, the way we can distinguish, because room modes don't change. Reflection-based anomalies will make the frequency change, okay? Cool, so try this moving exercise. You will see that, everything in mids and highs, even low mids, is a mess. You can't really detect much, but it should be possible to detect this notch. Now, you can do that in advance, kind of prepare yourself in terms of your expectations in the room simulation. So what I can do here is I can remove the modes, and what I can do is move the speaker. Okay? So there's a few things to do. So I will have to put a microphone down. I'm not sure why it's disappeared, to be honest. Here it is, right? So you can move the person and you can move the speaker. Okay? So with this bit, what I suggest you try is, first of all, remove one of the speakers. So here, first of all, remove the sub. Okay? If the sub is there, it's much more complicated because there is a crossover frequency, the speakers are cut, the position of the sub will change a whole lot. You can play with these things in terms of what you expect to happen. For this exercise, please remove the sub and remove one of the speakers, okay? Because we're looking at unnecessarily complex things. And then you can try to mimic the setup in the room. Obviously, by that time, the room should be matching already. So what I suggest that you look at, for example, is that, let's say the distance to the rear wall is 0.5 meters, about that. And then see what happens if I move the listener. Okay? So what you see is that this notch, I'm looking at this notch here, is not moving. Why not? And this is a question that I will reward with a can of beer next time we're doing the track attack. Why isn't the notch moving when I move the little listener back and forth? I mean, obviously I'm not doing it exact, so you see a bit of movement. It is supposed to be the back wall thing. Why not? So think through, what was the main cause for this type of anomaly? The two-word syntagm that I was repeating at the beginning, path difference. Can you think this one through?
Is it because the path difference on the sides isn't changing?
Not on the sides. The actual path difference to the back wall is not changing. Do the math, right? So if I am a meter away from this wall and the speaker is 0.5 meter away, right? My distance, the direct path is 0.5 meter. The path difference, the reflected path first, is 0.5 meter to the wall, 1 meter to myself, 1.5 meters. That is the reflected path. The path difference will be 1.5 minus the half, so the path difference is 1 meter. If I move away, if I'm at 2 meters, 2 meters is the direct path. The reflected path is 0.5 meter to the wall, 2.5 to me. 3 meters path difference is the same value. So if I'm actually moving away from the speaker in a straight line to the wall, back and forth, the path difference is not changing. The path difference will always remain the distance to the back wall, because I'm subtracting my distance from itself in this equation. Make sense? So that's one thing you can verify, hopefully, that going back and forth should not make this frequency notch go up and down in frequency. But if you go right and left, you see? If I go right and left at the same distance, then the geometry is such, you see that the reflected path and the direct path, they become these weird triangles, and the path difference is changing. So the path difference is the very crucial term to acquire and understand at this stage. Okay? So that's one thing that you can try to identify. And then the other thing is that if I am moving the speaker, this is what happens. Okay? So the notches are moving in frequency. Now you see there is many things happening simultaneously, and this takes into account the room modes as well. So it is not very easy to trace a single notch that goes up and down. But one way to do it is to think of the shortest possible path difference. When do I get the shortest possible path difference?
In the direct.
Where is the speaker for me to obtain the shortest possible path difference? Straight against the wall, right? If I have the shortest possible path difference, what do I expect to be the frequency of the notch? Very high, right? So short wavelengths yield high frequencies, right? So if the path difference is the shortest possible, then I expect the notch to be at the top of my spectrum. So what I can do then, in order to even in this is actually a math model. So it's not even nearly as complex as what you're supposed to see in measurement. But if I put the speaker straight against the wall and start to bring it closer in, you kind of see that there is one notch coming down all the way. But, oh, I'm watching the notches, not the path, right? But you kind of see one notch fighting its way down. And obviously, when it reaches certain modes, you suddenly don't trace it. It's compensated for. Other anomalies are happening. But if you do this, you can kind of trace it coming down. And at one point, obviously, when the speaker is there, then I'm looking at the response of the speaker, right? Because then... Okay, so that's that. I will add one more exciting thing, which is a bit advanced, but for those of you who are really interested, I think it might open up further cans with worms. There is one trick which you can do with REW. I'll leave you to explore it. You can actually shorten the impulse response. So what you get, typically we were just looking at the spectral displays, right? And that's it, and we work away from that. But actually, you can go back and forth between spectrum and impulse response. And if you shorten the impulse response and look at the corresponding spectrum, you will not see many of the very late reflections. In fact, you can do the math here. So for example, I can actually take a near anechoic measurement down to a given frequency depending on the circumstances. So if I imagine a speaker and a microphone, shall I make sure this is, I'm suffering my, if I have a microphone and a speaker here in the middle of the room, as far as possible from any reflection, right? Let's say they're ½ meter apart. Now the nearest wall is, let's say, 2 meters, okay? So the path difference will be approximately how much? Well, let's say like the least distance should be 4 meters just to the floor and back. There will be more because it's triangle, but let's neglect that. So it's at least 4 meters. The direct path is ½ a meter. So the path difference is 3.5 meters. Which means that there is a time duration within which I will not receive any reflections. 3.5 meters, how much is that? So I get, for 1 meter, I get 1/340 seconds. So let's say 6 times that, which will divide the number by 60. So about 60, 1/60 seconds, right? So I have a 60th of a second in my response, measured response, which is reflection free. What frequency responds to this? It's actually 60 hertz. So in this scenario, I can actually measure my speaker anechoically because there are no reflections in the way. Okay? So actually there is always a way to sacrifice the low end in order to see more accuracy in the high end, because the later reflections will be excluded. So in the context of what you're going to try to do in a bit, you see, if I'm trying to identify this notch and I'm, expecting it to be above 100 hertz, then I can actually time clip my impulse response, and it will get rid of the late reflections and help me identify the notch. Okay, so this is just on the side for those of you with large open eyes. Don't worry, it's getting complex at this stage. By the way, it's useful to know that there are things that I might want to explore later on as well. But that's it for now, okay? So today there is no one in the tech room. Goodbye to online people.